Okay, let's start today's discussion. Today we are gonna start the chapter 2, which is the modeling in a frequency domain. We are gonna start with the frequency domain, and we are gonna see how we can use and what are the basically tools that we have in order to run the frequency domain over any type of system. First, we are going to focus on a mathematical perspective of that, and then we are going to move on to actual systems and solve some examples in upcoming session. In this session, we are going to our discussion would be fully like mathematical, and we are going to learn about one of the most useful techniques that we have in order to analyze any system. Now, we already talked about that, why we actually care about the mathematical modeling. Basically, as we said in a previous session, we need to gain some understanding about how the system would perform, which basically the mathematical equations, the mathematical modeling give us a sense, a direct sense of how the system would perform and how the efficiencies and how it would react to a certain specific input. And ultimately, it basically enables us to design the control system and analyze if our control system or any type of system that we have actually work, and is it stable or not, and how we would react to different frequency and different type of like a transient or a steady state situation. Now, as we said, one of the most popular tools that we are going to use in a frequency domain, we mentioned that before, it's a Laplace transform. This is very handy, very useful tool when we want to talk about the modeling and analyzing a system, especially in this course, control system. Now, this is, as you can see, is the mathematical definition of a Laplace transform. Okay, what it does is that when we have a time variant system, okay, meaning we have a equation, the governing equation of our system in time regarding the time domain, time change, so time variant system, and parentheses, we consider the system so far in this course the linear systems. We are going to mention some nonlinearity in some systems, but mostly we are going to focus on a linear system. So when we have a linear time invariant system, so we can run the analysis over those governing equation in time. But since we are talking about some differential integral equation, it's not going to be easy to run those analysis. So what we do is taking advantage of this method, the Laplace transform, we are going to transfer our equation, the governing equation, from time domain to what we call S domain. Okay, S domain, you might ask, okay, what the title of the chapter and discussion is frequency domain analysis. So what it means to have like an S domain. S domain is basically those S is actually frequencies of our system. But it goes beyond what you learn in like probably signal and system about Fourier series. Okay, when we talk about the Fourier series, we only consider the oscillation, okay, the oscillatory frequencies, the oscillatory vibrations, okay, which remains actually, which kind of like keep the oscillation through the time and through the system. Okay, so that's the focus of Fourier series when we talk about the frequency domain analysis. Now, we know that the system is not just about oscillation. We have some like damping kind of like effect in our system, or even like when we talk about the unstable system, we have some component, we have some reaction when the input, when we inject the input, the output would get out of hand and rise exponentially. Okay, in an unstable system, but in a stable system, beside the oscillations, beside the continuous oscillations, we also have some damping factor in our system. Now, that damping factor is another type of vibration. It is another type of basically response of a system. Now, when you talk about the Fourier series, okay, we only talk about the j omega. Okay, but when you consider that damping factor, now in frequency we also have another constant, okay, which is not oscillatory. This is, see, this has j in it, meaning it's a continuous oscillation. This one is a real number, meaning it's not continuous oscillation. It might have like an overshoot, undershoot, but eventually it would damp. Okay, so that's the difference. That's actually why we call S domain a frequency response. This is a general form. Now, Fourier series is one individual part of S domain when S is equal to j omega. Okay, so this is the definition of Laplace transform, okay, which is the Laplace of our function is equal to the integral from 0 to infinity of our time domain function times e to the power of minus st. The integral is over time. Now, I want to ask a question. Why the integral is over time? And why we only consider 0 to infinity? Anyone can answer that question? First of all, why we integral over time, over t? Any idea? What is the what? Sorry?
Because you have the frequency domain.
We want to go to the frequency domain. And that is actually an answer. What it means when we want to go to the frequency domain, we want to get rid of the time. So we integral over the time. So the time is not any kind of like a variable anymore. Okay. You know, so we put. Okay, let's open up another parenthesis. I already like if you pass the probability with me, we already talked about that. But let's talk about it a little bit more. Integral, okay, integral conceptually is averaging. Okay, is a memory of the system. When you want to average out a variation, you took an integral. Okay, and the difference between the actual kind of like mean value or average of the values and the result of an integral is a simple component, is a simple coefficient. Okay, and these two are basically proportional to each other. What's that coefficient? For example, if you have n samples and you want to average out, the average would be the summation of those values divided by that n. Right? Now in integral, you add all the values together, but you don't divide it by n. So that 1 over n is a coefficient that distinguish the average value from the integral result. So when you think about the integral, I want you to think about averaging out the variation. Now our variation is over time, so we averaging out the variation over time, meaning we get rid of the time. Does that make sense? So that's why we integral over time. Now, why from 0 to infinity? Why not from like minus infinity to infinity? Sorry? Time is always positive. This is a general conception when we talk about the physical system, because we don't have the concept of negative time, but that's not actually true. We have the concept of negative time in mathematical world. Okay, so, but since we are talking about a physical system, we are going to solve an engineering kind of like system, and kind of like the a circuit or mechanical system. We consider time that starts from 0, and since we wanted to like consider all the variations through the time, we go to the infinity. Make sense? Okay, so that's why we took the integral over the time, and we go do it from 0 to infinity. Now, why we do that? What is the significance? What is the use of Laplace transform? First of all, as we said, all the system that we are running in our electrical engineering or mechanical engineering, or any type of actually kind of like system, they normally are governed by some differential integral equations. Now, when I say differential integral equation, you might not see any like integral equation in your system. That's because we get rid of the integral by making taking another derivative out of our system. So we only have differential in our equation. Okay. So for example, when you have an L and C, and you wanted to like describe the voltage over L is L dV over dt. So it's differential, but when we talk about the capacitor, is going to be the integral. The current is going to be the integral of the voltage over time. But if we do another derivation, now the L1 becomes the second order differential, and we get rid of the integral around C. Okay, for the capacitor. So this is kind of like the governing equation, the type of governing equation that we have. But you already know, you already passed the calculus. It's not easy to deal with the differential equations, especially when the order of the system goes higher and higher. So it's gonna be crazy. And if you want to like deal with that, you have to like take care of like use Taylor series or any type of linear equation, which is very kind of like time consuming and very hard analysis. Now, Laplace transforms basically changes that differential equation to a very simple algebraic equation. So now you have just multiplication and summation and subtraction, or like division. So the four main mathematical operation. Okay, it's going to be very easier to kind of like analyze. Now, another factor, I don't know if you covered that in calculus when we talk about the differential equation. One of the most important and one of the hardest analysis over differential equation is when you have a discontinuity in your system. So, like for example, I assume that when you talk about the differential equation in your calculus, you always consider the f of t as a continuous system and a smooth continuous system. But that's not the case when we want to like generally analyze the system. You are gonna have like some input as like a step function, which is not continuous because it changed instantly from like 0 to 1. Or you might have like an impulse as your input. For example, when you discharge a capacitor in your system, or there is a temporary fault in your system, when you have like a surge of current or voltage in your system, then that's gonna be like approximately a delta function. Which delta function, as you know, is like the ideal definition of non-continuous and non-smooth kind of like function. So how we deal with that? There is some advanced technique, okay, to take care of discontinuity, but that's gonna be even like way harder than you already the technique you already have to analyze the differential equation. Like probably if you want to learn that, the only course that I know they teach those concept is a 6,000, 5,000 course in a graduate level in mathematics, which normally even the mathematical student don't go there because it's very kind of like crazy techniques. Okay, so we said that, okay, now the Laplace transform would help us to deal with those non-continuous functions. Okay, so that's actually very, very important. I hope you understand the significance of that. Another factor is that we said when we talk about the stability, we don't talk about the variation over time. We talk about the states that the system could be in, those states that either is stable or non-stable. So when we talk about the stability, we talk about the state of the system, not what would be the value over time. Make sense? Now, if you wanted to like talk about the state of the system, and as we said earlier, the state, if you wanted to like define it like very generally and loosely, is tied to frequency. Okay, so when we talk about the stability, we talk about the state which is governed by eigenvalues or frequency within our system. Okay, it could be the input frequency or the natural frequency of the system. Make sense? So you wanted to like run a stability analysis, you need frequency domain model of your system. Now Laplace will give you that. Okay, and okay, I already mentioned that this continuous and impulsive signal. So this is kind of like the significance and the use of the Laplace transform and why we actually care about that. Now, I put the Laplace table on the PPT. This is your cheat sheet. It makes your life way easier. The definition of is that integral, but when someone else's did the labor work and give you this table, so keep that in hand. Even in the exam, you are allowed to bring that table, bring it. Otherwise, you are gonna have like a very hard time taking those integrals. Okay, so someone else has did the labor work, take advantage of that. Okay, each individual type of function, if you take the integral, it would have a specific Laplace function in estimate. For example, if you have a delta, the delta Dirac function, the Laplace transform of that would be 1. Now you can take the integral easily, is that because that's the easy part. The integral of delta e to the minus st dt from 0 to infinity, the integral of delta is 1. So it's going to be e to the minus st from 0 to infinity. On infinity, this is 0. On 0, this is 1. So it becomes 1. Make sense? So if we have a ut, the step function, ut is a step function. So from now, we call ut as we consider ut as a step function. So if we multiply by anything, remember, it's a multiplication of that function to the step function. Okay? The integral of a step function is 1 over s. You can do that Laplace transform. It's going to be 1 over s. If you have t times ut, the step function is going to be 1 over s2, and you can read the rest. And I encourage you to at least try some of these and take the integral so you get familiar what we are talking and what are the meaning of these, and get familiar with driving those integral, okay? Now, Laplace transform has several properties when we talk about like a mathematical techniques. We already mentioned the definition is the integral of that function times e to the power of minus st remember that, okay, over dt from 0 to infinity. Now, Laplace transform is a linear kind of like transformation. Okay, what that means? That means if you have constant coefficients time the time function k times ft, that means the Laplace of that is going to be k times the Laplace of ft. So the Laplace of kft is going to be kfs. Okay, now another point. We show the Laplace transform with that fancy L, and we always mention the time domain with the lowercase for the function, so it's lowercase f, and the frequency domain, the S domain, with a capital letter. Okay, so don't kind of like mess up these two because it would kind of like create some confusion. Now, another part of the linearity is the summation. If you have two functions adding to each other, the Laplace of, for example, f1 plus f2 is going to be the summation of the Laplace of each individual function. So it's it is very handy. That linearity is very handy. Now, what if we have a frequency shift in our system? Now, please pay attention. Frequency shift in time domain is an exponential function. So if you have e to the power of minus alpha t, that means your frequency is shifting by alpha. Okay, so this is the concept. Now you can think about that. Why is that? Why that exponential function means frequency shift? And remember that the frequency is the state of the system. Okay, now if you have such a function, the Laplace of that is simply the Laplace of that f function is just s would be shifted with the same power, with the same coefficients of t in the power of that exponential. So it's e to the minus at. So the Laplace would be f of s plus a. Make sense? No. Now, what if we have time shift? So our f in time domain is going to be f of t minus a certain constant. Now, if we have that, it's kind of like the same as we talked about earlier. So in the Laplace transform, it become the Laplace of our function time e to the power of minus s time that constant. So this is the constant, okay? It doesn't change. And the effect of that on a Laplace transform is e to the power of minus that constant times s. Okay? Now, we have the scaling theorem. Okay? Is different from this linearity. This linearity, k is multiplied by the whole function. The scaling theorem is actually changing the scale of time. Okay? So, if you have the f of a times t, so you're scaling the time, okay, then your Laplace transform would be 1 over a times f of s over a. Now, think about it. You are multiplying the time by a. What that means? That means you're changing the frequency and basically shrinking the vibration. Does that make sense? So now S is divided by that A coefficient. It's shrinking the frequency. Make sense? Now, remember the definition. If S is shrinking, Okay, that means like there is a here, 1 over a here. What would happen to the integral? You are going to have a constant multiplied by that when you do the integral. Drive the integral, you're going to see that. So this comes from the integral, this comes from the shrinking. Now, when you have a differential equation, d of f of t is going to be s times the Laplace of f. Remember, minus the initial value. Okay, that's important. So if we don't consider initial value equal to 0, you need to include the initial value when you want to like take a Laplace over a differential component. Now, the second differential, it's kind of like the expansion of the one before. Is going to be s squared times the function minus s times that initial condition minus the initial of the differential. Consider that when you talk about the d square, you are talking about the d over dt of df dt. So this is like g of t. You know? So you are using this formula twice. Make sense? Now, this is where that comes from. And it's simple. You can expand that by this concept to the nth order of the differential. And if you have an integral, that means you have to divide the Laplace of the f of t times s. Now, look at this part. When you have the integral is over another parameters from 0 to t, because the whole thing should be the function of t. Think about that. When we talk about why we take a derivative over t when we want to like have a Laplace transform, same goes here. We want to have a function of t, so we take the integral over an auxiliary parameter to have the f of t. Is that clear? So this is the integral, and when we wanted to like calculate f of infinity in time, that means the limit of s time f of s when s goes to the 0, and the initial condition is limit of s times fs when s goes to the infinity. Are we good? These are the characteristics of a Laplace transform. These are going to be also very handy, so I encourage you to also have this table in hand when you want to like solve the assignment and in the exam. Okay? Now, let's talk about some examples. Let's find some of the Laplace transform of some of the function. What if our f of t is 1? Okay? So it means like a DC function, the constant value. Now, if you do the integral, this means the f of s is going to be the integral of 0 to infinity 1 times e to the minus st dt. What is the integral? Is going to be what? 1 over s, 1 over s or minus 1 over s? Minus 1. This is the multiplication of the t, right? Minus 1 over s times e to the minus t. Now, this is a minus from 0 to infinity. You can get rid of that from infinity to 0. Make sense? Now, what is the infinity part? Is going to be 0. What is the 0 part? 1. So 1 over s. Make sense? Now, what if we have a t? Again, we replace this one. Okay, when we have a t as our function, again, you can make the integral 0 to infinity t times e to the power of minus st. Now, do you remember the integral of f times g? How we did that? The uv, the formula is the integral of f dg or g prime is equal to the let's go f g minus the integral of g d f f prime. You remember the rules of integral? So if you apply that rule and took the integrals, okay, you are gonna find, and we wanted to like find the fg. You are gonna find that the Laplace of this is gonna be 1 over s squared, which we already had in our table. Now, come on, how can I delete those? It doesn't let me to delete. Let's. What about e to the power of at? If you put that in the integral, e to the power of at times e to the power of minus t dt, you can mix these two, right? So now it's gonna be e to the power of minus s plus a minus s times t. You have to have a minus, so it's become e to the power of minus s minus a. Okay, and if you do the integral, it's gonna be 1 over s minus a. How is that? We already took the integral of 1 times that exponential. Correct? You can simply consider this as another value like p, and now we already have this. It's gonna be 1 over p. What is p? S minus a. Make sense? Is that clear for everyone? If you have any question, let me know. Are we good? Now, what if we have a cosine? Again, you can solve that. Now, you have two ways to solve that. One is to solve the cosine as using this integral of fg. Okay? Another part is that we know that we can consider the cosine as the combination of the two exponential. You can define cosine by exponential function. Okay? So either way, you can run the integral and have the Laplace transform of a cosine, which is s over s squared plus omega squared. And omega is what we have here as a coefficient of time. Is that clear? Is that clear what I said about the two-way of calculating the integral? Right? Okay. Now, how about e times the s omega t? How we can deal with that? Let's run the integral. This is going to be 0 to infinity e to the power of at sine of omega t e to the power of minus st dt. Now, these two are exponential. We can mix them. So it's become actually the integral of sine of omega t e to the power of minus s plus a t dt. Now we have another state function, a state variable. We can consider it as a p. Okay. Run the analysis for a simple sign, which we know the, let me see, the Laplace transform of, when we have Laplace transform of sine of, let's go back to the table. Oh, now it's clean now. The Laplace transform of the omega t is omega times s squared plus omega squared. Okay? Now let's go back to the example. Now this one is omega squared. Something is missing. No. Omega over the p squared plus omega squared. What is p? S plus a squared. Make sense? Now, what if we have t minus? So we have a shift in time. We already covered that. Okay, we can use those theorem that we said. Okay, you can use also the integral, and you would find that is going to be e to the minus as, which was the effect of time shift, remember, over 1 over s squared. Is that clear? So this is another example. Let's move on to another example. How to run Laplace analysis over a differential equation. Now, the Laplace of that x, let's say prime, of t is going to be the integral of 0 to infinity that x prime of t e to the power of minus st dt. Again, we have fg. Okay, we can use the mathematical definition of when we have like we wanted to like get an integral of multiplication of the two function. It's gonna be time consuming. I don't want to like get the whole differential right now, or whole integral right now, but you can do that. So the answer, if you have that, will be s to the x of s minus initial condition. We already mentioned that when we talk about the characteristics of the Laplace transform, we said if we have a differential of a function, the Laplace of is going to be s times the Laplace of that function minus the initial condition. Now here our initial condition is x0, so we consider that as initial condition. Again, if we have the second order, you can run the integral or use that characteristics, that table, and we know that the Laplace transform of a second order differential of x of t is going to be s squared times the Laplace of that function minus s times the initial value of that function minus the initial value of the derivative. Is that clear? So we use that. You can run the integral. Is this the same as this one? Okay, and you can find how each of these components came from. Okay. Now, what if we have an integral over auxiliary kind of like parameters in time? Now what's going to happen? this is a good idea. This is a good part to actually talk about another theory in mathematics. So let's do the integral. I don't want to miss anything. Now, the integral of that function, f of t, is going to be the integral from 0 to infinity of the integral of x of tau d tau from 0 to t and all of it dt. Okay? Now, there is a theory in math named Fubini that allow us to swap the place of the variables in integral. So we have tau and we have t. Here we have 0 to t, so the integral is over time. We can swap it by changing it to the integral over tau. Make sense? Now, what's going to happen is that, pay attention. Originally we have time goes from 0 to infinity. But tau goes from 0 to t. So tau is between 0 and infinity. Correct? So if we wanted to like change this part from t to tau, now instead of 0 to t, what we have to do? What is the margin of t? What is the lowest value of t? No. Tau. So it's going to be the integral. This one is going to become the integral of 0 to infinity, integral of x of tau from tau to infinity. Now, d tau dt. Oh, there is an e to the power of minus st. Sorry. Now, this is the integral over t, correct? This function, e to the power of minus st dt, this is also the part of the integral over t. So I can swap the places now. So it's become the integral of 0 to infinity x of tau integral of e to the power of minus st dt from tau to infinity. Okay? Now, what is the result of this integral? Oh, sorry, this is d tau, and this is dt. Yes? No. Sorry. What is that? It was e here, we change that. We change that variable. So now the Laplace of this part, the value of this integral, if you run the integral, is going to be e to the power of, this is x tau, e to the power of minus s tau over s. Do you know what that came from? Do the integral over dt. The integral of minus s t is going to be e to the power of minus st over s, right? So now we are going to do the integral from tau to infinity, put these values. This is minus, so it's going to be 0 minus e to the power of minus tau, which is plus s over s. Make sense? How we did the integral? So this is the result of the integral, the inner integral. We put that here. Okay. Now Now we have another Laplace. Now we have another Laplace. This S is a constant considering the integral is over t. So you can bring it out. Okay? This is tau, x of tau, e to the power of minus s of minus s tau, d tau. Correct? So this is another Laplace. It's Laplace of x tau. Correct? So it's going to be 1 over s, 1 over s times x of s. Does that make sense? Is it clear? I wanted to like make sure. So what we did is that we had x tau, two integral, x tau d tau from 0 to t times e to the power of minus st dt from 0 to infinity. We swap the t and tau, okay, using the Fubini. So now is integral of x tau d tau e to the power of minus s t dt. Now t is varying between tau and infinity. We swap the places of e and x. Okay, is going to be x tau, the e to the power of minus s dt. We are going to do the integral over time, which give us the value of e to the power of minus tau s over s. Now when we put this one here, we have the integral from 0 to infinity x of tau e to the power of minus s tau over s. S is irrelevant when we talk about we are doing the integral over t, so it's just a constant. We bring it out, and now we have x of tau times e to the power of minus s tau d tau, which is the definition of the Laplace transform of x of tau. Are we good? So now the result would be 1 over s times the Laplace of x tau. Is that good? Now, same goes for this function. Now, instead of x, we have sine of t. So we know that the Laplace of the sine is 1 over sine of tau is 1 over s squared plus 1. The coefficients of the variable is 1. Are we good? So using the derivation that we already did, the Laplace of this integral is going to be 1 over s times that 1 over s squared plus 1. Good? If we have time t times e to the power of minus at, we said we have both t and the shift in the time, sorry, the shift in the frequency. Okay, if you do the integral, this e to the power of minus at is going to be mixed, but that e to the power of minus s, so it's become t to the power of e to the minus s plus at dt. Now, if you consider that as p, it is the Laplace transform of t, which is 1 over s squared. Sorry, p squared, because we have p here. And p is s plus a. Are we good? So this is where that characteristics of frequency shift came when we talk about that, when we review that table. We derive the integral is going to be there. What about the convolution? Now, an easy way to remember when we have a convolution of the two function, I don't know if you know the convolution or not. Do you know the convolution? Okay. I already put the definition here. Okay, it's going to be x of x convolution h is going to be x of tau times h of t minus tau d tau from 0 to t. We are going to get rid of this tau. Okay. Now, the Laplace transform of the convolution is simply multiplication of the Laplace transform. So if you have x of t convolution convolved with h of t, the Laplace transform is going to be x of s, h of s. You can run the integral over that, which is quite of a derivation. It is the same kind of like concept of when we use the Fubini. So I encourage you to do that. I'm not gonna because it takes a lot of time to drive that uh, integral. But a shortcut to remember is that when you have a convolution in Laplace become multiplication. Okay, remember that. That's important. And search about the concept of convolution. Convolution is not just a very kind of lousy kind of like or like very complication of complicated mathematical kind of like operation. It means a lot in physical system. Okay. Now, what if we have a integral differential equation? How we can drive the Laplace of that? We have d over y, the differential of y in respect to time. We have the integral of y, okay? And it is all equal to a step function. This is the governing equation of our system. What if we want the Laplace of y, the function y? So we know that the dy over dt, the Laplace of that is going to be s y of s, correct? And the Laplace of the integral is going to be minus the initial value. Okay? We shouldn't forget that. The Laplace of the integral is y of s over s. And we remember the Laplace of the step function is 1 over s. And we know that the Laplace is a linear transformation. So if we have a summation of different Laplace, different function, the Laplace of them would be the summation of the Laplaces. Okay? So it's going to be sys minus initial condition plus ys over s, the integral one, is equal to 1 over s. Now it's a very simple algebraic system. Okay? So you can basically calculate. I made a little bit of mistake, I think, because the initial condition is missing. Let's solve that. It is going to be 1 over s plus the initial condition, and it's going to be s plus 1 over s ys. So now this is going to be s squared plus 1 over s. We are going to time this one. This is going to be 1. If you move this one, this is going to be s omega 0. And this is going to be 1 plus s y of 0 over s squared plus 1. Okay, sorry, can't disregard this one. This is basically, this happened when omega, this is 0, okay? Oh, I already have that. Oh, sorry. Okay, so this is going to be the general. So that was actually correct. This is correct. This one is correct. How can I eliminate those? Oh, okay, I'm learning. So this is correct. This is the general function. Since we define the initial value as 0, now it becomes 1 over s squared plus 1. Okay? Now, what if we want to go in the opposite way? Now, this one is easy because we already have the cheat sheet in the table. So if we wanted to like find the Laplace inverse of 1 over square s squared plus 1, we know this one is sine of t. If that one is omega, it becomes sine of omega t, okay? Whatever is here is going to be the frequency, is going to be the multiplication inside the sine, okay? So we know based on the cheat sheet, it is going to be sine of t. Now, let's talk about another example. How we can drive the Laplace over this one. Again, we already know that. This one, the Laplace of this first term is going to be s squared y of s plus s y of initial value of y plus initial value of y prime. This one is going to be 12 times s y of s, okay, minus the value of initial value of y, and this one is going to be 32 y of s, okay, and this one is going to be 32 over s. This is a step function. Now you have all the term. It's just the summation. Is a simple summation, algebraic summation of all those components. Okay, if you do that, it's gonna be like this. And this is we consider both of these initial values as 0. So this makes it a little bit easier. So we have s squared y of s from here. If they are not 0, you have to include that. Okay. This one is gonna be 12s y of s. This one is simple, 32 y of s, and this one is also simple, 32 over s. Now, again, you can calculate the y of s. Are we good? Now, this is the fun part. How you can calculate the time function of a Laplace transform when it has multiple poles. We call it poles. We are going to talk about that, meaning multiple terms in the denominator. Okay? Now, the first step of solving such an equation is to first take apart all the components. You know, this one, when you have multiplication of several terms, it could be like it actually originally was the summation. You can transfer this to a summation of some fraction, each of them with the denominator of those parameters, those terms. So this could be kind of like transform the summation of k over s, the first term, k2 over s plus 4, the second term, and k3 over s plus 8. This is how you transfer the simple fraction when you have the multiplication of several terms in the denominator into the summation of fractions, each with an individual term in a denominator. You know how to transfer this one to this one. It's the reverse. Are we good? Now, these k's are some constant. How we can find them? Did you learn how we can find them before? Now, when you wanted to do that, when you wanted to like do the k1, you eliminate the denominator regarding the k1, and the 0 of the denominator is when s goes to 0. So You eliminate this, it's become 32 over multiplication of these two terms. You limit, you send the s equal to 0. Whatever happens, whatever value we have, is going to be the k1. Same goes for the other one. We eliminate this one. For this part to become 0, s should be minus 4. So we put s minus 4, we do the calculation, we have k2. Same, we have k3. So now we have three separate ys, and we know the Laplace is linear. Okay, so we can individually take a Laplace inverse, and the result would be the summation of those inverse. So very easy. Are we good? So this is for today. Do you have any question regarding the Laplace transform? We introduced the Laplace transform, that integral that says the Laplace of f of t is going to be the equal 0 to infinity f of t e to the power of minus st dt. That was the definition. Okay. We covered the characteristics of the Laplace transform, the linearity, the scaling, the multiplication, the summation, if you have a derivative of the f, if you have the integral of the f, if you have the convolution of two functions, what you can do to take a Laplace transform of that. We talked about the time shift, we talked about the frequency shift, we saw several examples on each of those concepts. Okay, so I want to assume from now on that you already know how to take a Laplace transform. Okay, you have the cheat sheet, that table, and those characteristics, the two tables that I put in the TPT. Okay, so you can use that, but I encourage you to, at least for the beginning of the semester, try to run those integrals. So basically, you get fluent on how to run the integrals. Okay, so it would be you would be familiar, and it would be easy to handle for you to actually drive the integral from scratch. Okay, and find the Laplace transform from scratch. Are we okay? Any question? No? Thank you. Thank you very much. I see you on Thursday.